one thing is about the brackets, the square.
Uh-huh.
That's just dot product, right?
That's right. That's
Okay.
just
All right.
dot or inner product.
Okay. Yeah, there's no difference between dot and inner product, right?
That's right.
Okay.
So
That
it's
makes things a lot easier.
it's called inner because it takes two vectors and makes a number out of it.
Oh.
Kind of collapses vectors to numbers. And it's in vector case. In the functional case, that's what we use. It's the integral over the space. And in one dimension, it's integral over dx from minus infinity to plus infinity. The left one conjugated, the right one is taken as is, right? Now if we work with, say, function 1 of two variables, x, y, and function 2 of two variables, x, y, then this notation, what it actually means is quite conveniently, you don't need to write the integral, but the integral would be a double integral for both variables, dx dy, and then the internal part is the same, f1 xy times f2 xy. So that way you can go from one variable to 2, 3, and as many number of variables as you want, as you need in your consideration. Because in quantum mechanics, if you have one particle in three-dimensional space, one particle, three-dimensional space, that means you need x, y, z coordinates. And so far we've been working only with the x-coordinate as a spatial coordinate. That's not because everything is one-dimensional in quantum mechanics. That's just to make the illustration simpler. Okay, but in reality, even if you consider in one electron, you need to, wherever we put dx, you need to consider dx, dy, dz in real situations. So now, in this class, we'll be working a lot with one-dimensional problems, so that you can kind of get the feel what is quantum mechanics is about, rather than focusing too much on the math of multidimensional integrals. Okay, but again, the reality is a little bit more complicated, because even for one particle you need 3 coordinates, and for 2 particles, if you have 2 particles, then in quantum mechanics we need x, y, z for the first particle, and x2, y2, z2 for the second particle. So in total we need 6 coordinates. And these integrals in the inner or dot product will be 6-dimensional integrals for 2 particles. And so things grow very quickly with the number of particles. So if you have n particles, then you need to multiply by 3. That's the number of variables you need to deal with. And of course, if it's not for this notation, I would be spending most of the time writing the integrals and coordinates for those particles if I consider, say, realistic molecules, right? So that would not be fun. So thanks to mathematicians and Dirac in particular, who came up with this notation for quantum mechanics, and this notation allows you to kind of ignore or forget for some time what's the space you're working in, and you're kind of only considering some kind of states and functions without really thinking what's the space, what's the dimensionality. And there is a more fundamental reason why this is useful, because functions, usually you think of them as functions of like x, y, z variables. On the other hand, you can present functions also as a linear combination of other functions, and so then in that representation the function is presented as coefficients in that expansion. Okay, and so the point here is that in this representation you do not specify what is the dependence of the function. Is it on x, y, z, or the coefficient in the expansion of the function as a linear combination of other functions? So it's more, essentially this representation is more general, more abstract. That's why it's more difficult if we go really into the details of that. All right. So for now and for this class, all you need is to understand that whenever I write this, that means it's just integral, okay, over the space, and usually the space is one-dimensional. I will consider in future a couple of examples. Like the final example in this course will be hydrogen atom. There we'll have 3 dimensions. So this type of inner product or dot products will be over 3 dimensions. Okay? Any more questions? So, as you've seen already on what I posted today, the idea is the following. So hopefully at this point, if I give you a wave function of the quantum system, you will know what to do with it, in the sense that if you're interested in certain properties, then you know how to predict from the knowledge of the wave function what will be the results of the measurement. Okay? And let's just review this, and we will move on to the question, how do we find this wave function, right? So that's the topic of today's lecture. How do we solve time-dependent Schrödinger equation to obtain this function? But before we move on, let's just quickly review. Say, if I'm interested in property for this kind of specific example, let's say if I'm interested in potential energy, right? And the question is, please predict me the result of the measurement for potential energy. So how would you do that? You have a wave function, yeah. Right, so what is the operator here? That's right, so if you have a property, then there is a always operator associated with that property, in this case potential energy operator, which is just multiplication by the function. And let's say for, again, restricting generality here, but to make it concrete, for harmonic oscillator case, for example, you can say that the potential energy is this function, harmonic oscillator. We'll study it later. Right now is just to have some function and not to scare you with the just abstract notation of some function of x, so that here's the particular function, right? And so here's an operator, as was pointed out. Step number, well, this would be step number 1 actually, to define what is an operator, right? And the second step, if you have an operator now and a function, you check whether this function is an eigenfunction of the operator. Okay? And so if you multiply any function by omega square x squared divided by 2, or any normal function is not going to be a constant multiplied by a function itself, right? So the answer is no, right? So it's this normal, well, let's say, to be specific, the function would be the exponent of minus e I t, and multiply by sine of pi x divided by 2 when x is between 0 and 2. right, and 0 otherwise. Right, so if you have that function, you multiply it by x squared. It's not the same function multiplied by a constant. Very simple, because you multiply it by x squared, not by a constant. So the answer is no, so what do we do then? I'd say it's normalized, yes. You can check it. In this case, it's normalized. Yeah. Coefficients of what? Coefficients of what? You said we should get the coefficients. Eigenfunctions of what? Of the operator. So step number 3, we find, or someone gives us, and in this course I usually will always supply you with the eigenfunctions of the operators, or you will know them from the previous examples. So it's not that you should expect that I always supply for the cases which we study already, like kinetic energy operator. You already know what the eigenfunctions are. So in this case, let me not detail what the eigenfunctions are. They are a little bit more complicated in this situation with the potential energy because they involve Dirac delta function. But at any point, let's say they exist, there are some eigenfunctions, and then we need to find the coefficients of the expansion, right? Of this eigenfunction. How do we find the coefficients of the expansion? And why do we need them? All right, so the next 2 questions, right? How do we find them, and why do we need them? Okay, so this is the scheme actually at the end of this semester, at the end of this course. You should really know, even if someone wakes you up in the middle of the night, because this is crucial. We've been through this many times. I hope that you just need to refresh your memory, but this is the key, one of the key schemes. This is the core of the quantum mechanics. If you don't get this, there is no excuse. Essentially, you wasted the semester. Okay? Yeah.
To find the coefficients, you have to take the integral of the wave function times I forget the word inverse to start.
Right. So this is pretty much inner product of Fn with the wave function, right? So now, why am I so adamant about you knowing this? Because in reality, think about it. You study a subject, and the main outcome of this subject is ability to predict experiment. If it cannot do that, there's no point of quantum mechanics. It's just a complicated math. Like, why would you waste place in your brain memorizing complicated math? That's just stupid, right? So, but that's the main value of the quantum mechanics, that they can predict experiment. And you, as a kind of person who studies the quantum mechanics, need to know that's the most valuable part of the quantum mechanics. Otherwise, it just makes no sense to study quantum mechanics, right? So we got these coefficients. Presumably, you all know how to calculate the integrals. So what do we do with these coefficients? What's the value of these coefficients? Why did we find them? What do they mean physically? As a result, like when we study this scheme, wave function, we do measurement, what happens? we get number, right? So in any measurement, just you don't need to study anything. It's like from the kindergarten. Whatever measurement you do, the result is always a number, right? So what else is the result of any measurement? Is a number. So then the question is quantum mechanics. What number does it provide as a prediction? For that, you don't again need to be smart. All you need to just look at this and see where the numbers are. Is this a number? What is it? It's a function, right? Is this a number? No, it's another function. Where is the number here? It's lambda, but this is not equal to that, so that's why lambda is not relevant. Do we have any other numbers here? Coefficients are numbers, right? So can coefficients be the result of experiment? Yes? No? Who thinks yes?
There's some likelihood. There's some probability that will be the result.
Okay. Well, we'll get to that. But coefficients, like based on my simple logic, coefficients are numbers, right? Why can't they be results? Like I'm just thinking very, like imagine I forgot whatever was in the previous lectures, and just based on the simple logic, I'm looking for numbers, right? So numbers will be the result of experiments. So coefficients are numbers. Can they be a result of the experiment? Yes? No? Okay, let's not cross them out, right? So they can potentially be. Do they have other numbers? Because if they are the only numbers, then that's the solution, right? So it must be right. Do we have other numbers here? What about lambda n? Are they numbers? Okay, so they can be other candidates, right? Now, good, we have two candidates. Like Hillary and Trump, right? Two candidates. Let's decide which one is the right one. So what about this guy? So coefficients, they can be like, okay, so numbers can be different. We talked in the beginning of this class that some numbers can be complex, right? And there is a problem with those numbers. They are needed to complete the picture, say, if you want to solve for quadratic equation or some other equation. They kind of complete the picture of, that's called field in mathematics, right? So field of numbers is complete if you can present the solution of any algebraic equation from the same set of numbers as the coefficients. And complex numbers arise like that. But they cannot be results of the measurements. Like you will never measure like how much water do I have in this cup, which will be 1 liter plus 5 imaginary liters, right? So it's always kind of number of liters, number of milligrams, or whatever, right? So any measurement should be represented by a real number, and it could be positive, negative, but it should be real. Coefficients can be complex, so that's why they cannot be a result of the measurement. And more than that, there is a theorem that says that lambda n's for all observables, they are real numbers and they are the results of the measurement. So it's not much to ask, right? So it's a very simple scheme. You have a property, then in quantum mechanics any property has an operator, any operator has an eigenfunctions and eigenvalues. Eigenvalues are the results of the measurement. Very simple. Because they are the only numbers that can be real. Right? So keep it real and things will be easy in quantum mechanics. Right? So these are the results of the measurements, the only one. The other possible outcome of this check is that when you operate with the operator on the wave function, you get number times a wave function, then that number is the result of the measurement. But this can be also considered, this situation can be considered as a subcase of what we are just considering now, the situation where wave function is not an eigenfunction of the operator. Then we do the expansion over the eigenfunctions. And as was pointed out before, the coefficients are not that useless because there are potentially many numbers like that, right? But whenever you do experiment, you get one number. Okay? All right, so here you get the set of numbers. So how do you choose between them? Okay, that's the second question that arises here. And that question makes us go back to coefficients and consider, okay, so then maybe there is some use in those coefficients. And it turns out the coefficients, because they're complex, they cannot be used by themselves, but if you take the absolute square of those coefficients, that will be the probability of finding in any single experiment a particular value of lambda. Okay, so that's kind of a general structure, which you will practice more in homework. I think even the homework I gave already should have some problems where you do the expansion, find the results of the measurements and coefficients. Okay? Any questions? It's crystal clear, right? All right, now let's talk today about, now you know what to do with the wave function. Maybe you will need to learn a little bit more operators that if you're interested in certain property. But of course, this all will be useless if I don't teach you how to find the wave function, right? Because then there's nothing to work with if you don't know where the wave function is. Okay, so this wave function, the good part is that it just comes out of the equation. And the equation is time-dependent Schrödinger equation. We wrote it already, but we didn't go into the solution. Okay, so and writing this equation is the simplest part of quantum mechanics because it's relatively straightforward even for molecules. I'll teach you how to do it for molecules a little bit later, but let's say for a single particle, you will always in one dimension have something like kinetic energy part. This is T part plus potential part. And potential part can be of two kinds. All right. So one is it has time dependence. That's the most general situation. And physically that corresponds to having a particle and some time-dependent field affecting that particle. So one could think of electron and electromagnetic light, all right, electromagnetic field that comes and starts interacting with the electron of your choice, all right. But this is somewhat more complicated situation. What we will be looking at is actually simpler situation where this potential will depend only on space coordinates, okay? And no matter how complicated molecule is, there's always a way to write this potential term as a function of coordinates of the molecule parts like electrons and nuclei that form the molecule. And in any molecule, you don't have time dependence. Okay, so time dependence only comes if you have electromagnetic field, laser say, that interacts with the molecule. So all sorts of spectroscopic problems when NMR, IR, they require time consideration. And that will be a subject of, say, C-level course, C20 or C21 we have in our curriculum. And if you're interested, you can sign up for those courses. And there I talked about time dependence and how it can be treated. But in this course, everything will be very simple. We essentially have two operators in our Hamiltonian, kinetic energy and potential energy, and they are time independent. Okay? And this is a very important point here. And I'll be asking you in exams and mainly on exams and homeworks, is when can we do what I am about to do now? what I'm about to do is to simplify the consideration of the time-dependent Schrödinger equation, and I will show how to reduce the solution of time-dependent Schrödinger equation to solution of time-independent Schrödinger equation. And it's only possible if we assume that the potential is time-independent. Okay, and you will see in a moment why. So now the setup is that we have h that depends only on x, and we have we can write down this equation in the following way, in the operator form. Okay, so this is an operator acting on our function and giving 0. Right? So it's clear, right? So what I did is I moved this thing, the right-hand side, to the left, and I wrote it as an operator of h acting on function psi minus operator of t acting on psi, right? And since nothing is left on the right-hand side, then I can write 0, right? Okay, so also I can write this as 0 multiplied by a wave function. Why would I do that? I would do that because then it looks like, algebraically, without going into the details, it's like I have two operators, some of them, which can be thought as an operator of x and t, right? But we know the structure. It's, as we will call it later, separable operator. Separable means that it can be broken to two pieces. One depends on x, another depends on t. And that's what we're gonna use. But more importantly, so what do we have? We have an operator acting on a function, and in this form we have an eigenvalue problem, right? Meaning that operator acting on a function gives us eigenvalue, which is 0 multiplied by the same function. So technically we have an eigenvalue problem for the time-dependent Schrödinger equation. And in the situation when potential is not dependent on time, we have operator to consider which is separable. So it has two parts. One is x part, another is t part. And here there will be a magic. Okay? So magic is the following. I'll magically tell you what is the solution for such eigenvalue problem. It turns out that I can always write the eigenfunction as product of two functions. And one is x function, another is t function. Why can I do this? Because the operator that I'm considering is a sum of two parts. Alternative would be if I had an extra term which would depend on both x and t. Right? So if this was to the truth, right? So if I had this type of terms, this one, and this one, then I would not be able to do this. But because I don't have this term, because, well, possibility for this term would be if I had potential that depends both on x and t, but I don't, so nothing to worry about. Because my operator is just x plus t part, I can always write the function, which is an eigenfunction of this operator, as a product. And now there is a simple proof. Magic is over. Now I'll kind of review why this works. And it works for the simple reason. So we have what? We have h plus this theta acting on, say, let's just check, phi theta, right? So how this sum will act on the product? Well, one by one. So first we'll have h acting on phi theta, and then this big theta operator will act again on the product. Okay, nothing surprising here. What we should now consider is that h depends on x, right? Phi depends on x, theta depends on t. And so when h acts on the product of these two functions, phi and theta, it will only actually affect phi, because theta depends on t, and t is not part of h. So it's like, simple example would be the simplest operator in x, differentiation, and if you have a function like x to the power of n, exponent of t, right? This part is like a constant to derivative, right? So derivative doesn't do anything to this part. And this exponent is a kind of example of theta function, and the x to the power of n is an example of phi function. So then what we have here is that we can move theta in front and leave h with phi as an entity. Now what I forgot to say, and which is very important here, is that for this to be true, phi and theta must be an eigenfunctions of this operator and that operator respectively. So what I mean by this is h phi is some kind of, let me stick to my notes so that, yeah, so that the notation will be the same. Let's say h phi is e phi, right? So phi is an eigenfunction of h, and also this theta lambda theta, right? So the theta function is an eigenfunction of this operator, right? So the whole kind of statement is that if you know how to solve problems separately, then all you need is to take functions from the separate problems, multiply them, and you get the function which is an eigenfunction for the sum. Okay, so that's the part that we are now will illustrate by construction. So as I already explained, that h acts only on phi, and we know how it acts on phi because phi is an eigenfunction, right? So we have e phi times theta, and e is a constant here. And then let's see, what about this case when the theta operator only acts on t. More than that, it's actually constant times the derivative of t, right? So then naturally it will skip the phi because phi depends on x, and that means that phi of x is not really a function for this operator. It's like a constant for this operator, right? And so then phi theta kind of skips phi, and when it acts on the theta, it gives us lambda, because that's the rule how this operator acts on theta, right? Now lambda is also a constant. Okay, now let's just group all the constants together. E plus lambda will be a constant, and we have initial product, right, multiplied by that constant, e plus lambda. So let's see, what did we start with? We started with two operators, h plus theta, acting on the product of their eigenfunctions, phi for h and theta for theta, right? And what we found at the end is that, well, this product is itself an eigenfunction, because we recovered back the function, and the only change that these operators produced is this constant, which is the sum of two eigenvalues. Okay? Any questions? So that's essentially the key to this magic. By magic I call the fact that I kind of guessed what will be the solution of this problem, knowing the solutions of separate like eigenvalue problems for the operators that are constituting the total operator. Okay? So how does this help us? Well, obviously, all we need to do to solve this problem, or to solve the time-dependent Schrödinger equation, it is solving this problem and this problem. So we split one big problem into small problems, because this problem was looking for a function of both x and t, while these two problems, they are problems for the functions of x and the function of t. Okay? So whenever in differential equations, whenever you can break down two-dimensional problem into two one-dimensional problems, well, that's a big deal. Okay? Because solving one-dimensional problems is much easier than solving two-dimensional problems. Simply because if you look at the one-dimensional function, any one-dimensional function, right? So it's like function like this. You need to find the wiggles, and then there is another function of, well, say there are two functions like this, x and t, right? But if you think about two-dimensional problem, it's already like a surface, right? So that I don't even know how to draw it, right? So you would need to not only find one-dimensional slices, but you need to find all the internal regions, right? So it's much more complicated. Okay? So that's why this is a big deal. We split the problem to two. And more than that, it turns out that, let's start with the simplest problem out of two. This one is very simple. I will explain in a moment what does that mean. And also, you've taken physical chemistry before, right? Chemistry B20. Am I correct or not? Okay, so there, I presume you looked at the chemical kinetics, right? So first order reactions. So what is first order, like kinetical scheme of the first order is like A goes to B with some constant, right? And so then if you are interested in concentration of A as a function of time, then you can write differential equation. Did you write it? Did you consider differential equation for the first order?
K is equal to dA,
That's right, yeah, that one.
dA.
K multiplied by concentration of A with minus, because it kind of concentration is getting depleted, dA dt, right? So that's the differential equation. If you solve it, you need, well, first of all, you need the zero time concentration of A, right? If you know this, then you can write down that this is the concentration of A at later time. Essentially, you have zero order concentration. I keep saying zero order, zero time. This is time, this is this concentration at zero time. And then there is an exponential decay that was generated by this function, and you're supposed to know how to solve this differential equation, how to get to this point, right? So If you don't, then review it at home, and if you have troubles, come for office hours, we'll discuss that. Right now I will not stop at this point, assuming that you're more or less familiar how to do that, because what this equation is pretty much a quantum version of this, but the math is exactly the same. So let's just write it down. The theta operator, right? It's minus I h bar d over dt. And so what kind of equation do we have? We have minus I h bar d over dt acting on the theta t, giving us lambda theta t. And so after some rearrangement, which is, say, the d over dt equals to lambda divided by minus I h bar. Now, if you think about theta of t as a concentration of A, then this will be the analog of minus k, and then you have pretty much the same equation, right? So we can write it like this: d theta over dt equals to, now if we multiply by minus a the denominator, or by a I denominator and numerator, then we'll get I lambda h bar theta, right? So this is the equation, and this is just a constant. So the solution of this equation is theta of t equals to theta at 0, the exponent I lambda h bar t, right? So very simple. Now, going back here, one thing to notice is in the original time-dependent Schrödinger equation, what we want is to have eigenvalue equal to 0. Right? So everyone is done writing the time-dependent? Okay, so let me repeat. So for the time-dependent Schrödinger equation, what we're interested is to get the wave function with the eigenvalue equals to 0, right? Now, if we take a random product like this, where phi is an eigenfunction of h with e eigenvalue, and theta is an eigenfunction of theta with lambda as an eigenvalue, then when we plug it into the time-dependent Schrödinger equation, the result we get is an eigenvalue which is e plus lambda, right? Well, we needed 0. What does that mean? Well, that means, so to have a consistency between this and that, we still can use product, but there should be relation between e and lambda. And the relation is very simple. E should be equal to minus lambda, right? If e is opposite to lambda, then when you sum e and lambda, you get 0, right? So you have one number equals minus another number, right? So you sum them together, you get 0. Very simple idea here. So e should be minus lambda, or you can think of lambda being minus e. That's exactly the same. Now, why am I bringing this up? Because with that addition, let's say we would like to eliminate everything and leave e as the main eigenvalue in this pair. And so then the theta of t will be written as theta at 0 time multiplied by the exponent of minus I E time divided by h bar, right? So that's our time function, okay? So you see, we already done half of the work. We define what the theta function is. So all we are left with is actually defining what the phi function is. But you're still writing what I wrote, right? Although it's all in the notes. So, any rate, so the theta is found. The only thing which is left is to find phi. And phi is already, I formulated what the problem is with phi. Phi is given by equation that h acting on phi, which is a function of x, gives us e to the function e times function phi of x. And for the rest of the semester, what I will be solving is this problem for different systems. Why? Because this problem is the key to the solution of time-dependent Schrödinger equation. See, I broke this problem into something I know how to solve, and I gave you the solution, and something that is non-trivial to solve, but it depends only on the space variables, right? So no more time dependence in this problem. And that's called time-independent Schrödinger equation. Okay? And of course, different problems will have different solutions, and they all will be different based on the Hamiltonian. So we will study particle in the box, harmonic oscillator, hydrogen atom. They all have the same form, it's just the Hamiltonian will be different. Okay? And once we solve this problem, there is easy route to the full solution because we know what the time-dependent factor is. Okay, so the full solution can be combined like this. Okay? All right, now I think the only one thing is left. It's so-called superposition principle, but it's a very important point here. So right now I'll leave it as is, so I'm not going to go and solve this problem because simply I cannot. I haven't, like you remember when I was talking about H, we agreed that potential part will not depend on time, but I never defined what the potential part is. So if you don't have V of x, you will not be able to solve this problem, right? So particle in a box, harmonic oscillator, and other problems, well, mainly those two because they can be considered in one dimension. So the kinetic energy will be exactly this, but the potential part will be different for those problems, okay? And we will be looking at them more in details in the next lecture. But right now, what I want to emphasize is that this problem has multiple solutions in general, right? So that means you can have, well, like we saw before with kinetic energy has multiple eigenfunctions. And the Hamiltonian is, well, he's also an operator, right? And if V of x, say, is equal to 0, identically, that means for all x's. That's why I have triple horizontal bar, right? So then H is equivalent to the kinetic energy. And, well, that's why it's so natural that any Hamiltonian would have multiple solutions, right? And when you have a multiple solution, then you may ask, okay, so which one do I put here? Right? So far I was operating thinking that there is one solution of this problem, and I take it and put it here, and I have one solution of this problem, and I put it here. And so now it turns out that there are multiple solutions of the time-independent Schrödinger equation. So the question is, what do I do with that? Right? So which one do I take to construct this one? And the answer to that is actually quite simple. It doesn't really matter. And it's usually defined by initial conditions. What do I mean by it doesn't matter? It means that if I take psi of x of t, which is equal to the time-dependent part from here, so it's theta of 0, the exponent of minus here, e corresponds to some n, and n can be anything from 1 to infinity, 1, 2, 3, and up to infinity, right? So this is a time-dependent part, and I multiply it by corresponding phi n x. This function, when you put it in time-dependent Schrödinger equation, will be its solution. And we can check this. So if you take this function, put it in this equation, you will have left-hand side equal to the right-hand side, independent of what n do you take. Again, magic, but let's see how it works. So it works because when you put this and you act with the Hamiltonian on this thing, theta 0, the exponent minus I n t of h bar, phi of n x, right? When I act with a Hamiltonian on this complicated function, there is only one part that Hamiltonian will affect. Which part is that? You guys follow? Hamiltonian is x operator, right? So it only will act on the functions that depend on x. Now there are three. Well, this is a constant, this is a function of t, this is a function of x. All right? So the choice is obvious. Hamiltonian will only affect this function, right? And we know from this equation how Hamiltonian will act on this function. What will be the result of that action? The result will be constant en multiplied by the same function. Okay? So then we can easily write down what the left-hand side is, because the two terms out of 3 are not touched, and then there is a en phi n x, right? And so this is the left-hand side, this part. Now let's see what's the right-hand side. The right-hand side is I h bar, and we need to differentiate this thing. Differentiation with respect to time will affect only part that depends on time, which is this exponent, right? And we know how to differentiate the exponent. The constant will be left alone. The phi n of x will be left alone. And then when we differentiate d over dt, the exponent of minus I e n t h bar, what will be the result? The result is that everything but t, all this minus I e n divided by h bar, will be taken outside from the exponent, will be put in front, and then you can already see that en will appear the same way it appears here. The only thing that you need to be careful is algebra with I, h bar. But you see h bar here is divided, well, like we divide the expression by h bar, here is will multiply by h bar, so they will cancel each other. And then minus I multiplied by I will give us 1 because I and I minus 1, and there's another minus 1 here, so there will be plus 1. And so the result will be exactly the same. It's En theta at 0, the exponent of minus, the exponent never dies when you differentiate, so you should not forget about the exponent, and then there is a phi n part. Right? So if that was too fast for you, let me know. After the lecture, we can go again. Or in the notes, it's already kind of broken to pieces. And the main idea here, if you compare right-hand side and the left-hand side, they're exactly the same. Why? Because by construction H, what it does to phi n, it multiplies the whole expression by En, and similarly, when you differentiate the exponent of the time function with respect to time, En comes out the same way it comes out when the Hamiltonian acts on the spatial part, right? So that's the balance of two forces, the one that comes out of x dependence and another that comes out of t dependence. So any product like that is a solution. Okay? And you may be still unsatisfied with the kind of ambiguity that creates. So now, again, there are multiple products like that. Which one do we choose? Because we cannot say that the solution, like, yeah, we have multiple solutions, but reality is that for any quantum system you have a single wave function to consider. Okay? And so that wave function, now we go back to the what differential equation we solve. We solve time-dependent Schrödinger equation, and the solution of that equation depends on initial conditions. What initial conditions are is what is my function at 0 time. So that you need to know. Okay? That's it. So just to give you an example, in your beloved classical mechanics, if you want to tell me what's going to happen with this piece of chalk if I throw it with a certain velocity in a certain direction, what information will you need? You need, of course, the force with which I will throw that piece of chalk. You know the gravity, but more importantly, you need initial conditions. What is the initial position of the piece of chalk? What is the initial velocity of the piece of chalk? Because depending on those two parameters, the piece of chalk dynamics in time will be different, even with the same force, right? So the same here. In order to solve time-dependent Schrödinger equation, you need to know what is the initial wave function at 0 time. This is an analog of initial position and initial velocity of classical object. In classical Newton equations, you need to know where the object you are studying and what was the velocity in the beginning. Then you can solve the Newton equations and obtain x of t and v of t later time. That's the setup of classical physics. Quantum physics is no different here. The only difference maybe is that you don't actually need position and velocity, you just need a wave function at 0 time. And solution of time-dependent Schrödinger equation gives you the wave function at later time. That's what I showed you before when I was showing, okay, let's consider, say, a quantum system. It goes this way, encounters the potential, and then comes back. So I started with some initial wave function, and I was plotting the probability density of its dependence on time, right? So that's the object I was plotting. But of course, in order to do that exercise, I needed the wave function at the 0 time. Without that, there would be no initial setup. It's the same as asking you what's going to happen with the piece of chalk without giving you the initial position of piece of chalk, right? So then you will not be able to define what, even if you knew the forces. It's the same as like, okay, a very simple problem, no force but gravity. I just release the piece of chalk and ask you where is it going to be in 1 second. But depending on whether I start here or I start here, there will be different dynamics, right? So in 1 second, say if I start from here, it will be here. But if I start from here, it will be on the floor, right? So the position will be different depending on where do I start. The same here, the dynamics of the wave function will be different depending on what is the initial function. Now, superposition principle. We still have ambiguity because any product like this would work. So, but the initial conditions are, they help us for the what they help us with. Actually, we can present this function, because it has no time, as linear combination of solutions of time-independent Schrödinger equation. The same as with kinetic energy, Hamiltonian has an eigenfunctions and they form complete set. That means whatever function you are, well, like whatever function you started from, it can be presented as a linear combination, and the coefficients can be found in the same way we always we're doing that, right? So coefficients are just integrals of the solutions with the function at 0 time. Now, with that, what is the most important part here is that from the initial conditions we know what the coefficients are. And then knowing that at later time this is the form of the solution, then we need to say that, okay, if we want a time dependence, coefficients stay the same, yn stay the same, but then there will be I and t divided by h bar. Okay? So that is our wave function at later time. Why does this work? It's very simple. This pretty much, this theta thing can be considered the Cn, right? Because theta 0 is a constant, Cn is a constant. It's just the different names for the same thing. Now, what we did here, we added all possible products like that because they all solutions. We checked that they all solutions, right? And how do we add them with what coefficients? That is defined by initial conditions. Okay? And that's what constitutes the so-called superposition principle in quantum mechanics, is that like with waves, we have, this can be considered as an individual wave. Individual n can be considered as an individual wave because it has time and x dependence, right? So you can add waves together with arbitrary coefficients and you will still get the solution of the time-dependent Schrödinger equation. That's the beauty of it. And that's what makes the double slit experiment work, because you have waves going from two slits and they just add together at the end, destructively or constructively, and that's the total solution, which is presented with this sum. Now, the only kind of restriction to the ambiguity is, well, we need to know the initial wave function, and that's what sets the coefficients in which we kind of combine the individual contributions, right? So that's pretty much all. Now what is left is kind of two situations. As with measuring the operators and like properties, you can think of two cases. One is very simple case where you have a wave function as just a single product of space part times this time-dependent exponent, right? This is so-called stationary state. A stationary solution of time-dependent Schrödinger equation. And the second case is when we have Cn not equal to 0 for more than one n. So what does that mean? That means we consider in this sum where at least two terms are present like this. In this situation, in stationary state, we consider in only one product, all other coefficients, only one coefficient is 1, other 0. And in this so-called non-stationary state, non-stationary case, we have more than one product of the spatial part with the time exponent, all right? And that's called non-stationary state. Write it. Non-stationary state. So now I will explain you where do these names come from, okay? So let me remind you that in quantum mechanics, the wave function itself, although useful object, doesn't really mean much, because as we discussed, all the properties are coming as eigenfunction or eigenvalues of the corresponding operators. The only property that comes kind of naturally out of the wave function is the probability density, but for that you need to square a wave function, right? So this is physically observable property. It defines the probability density. The function itself is not physically observable, okay? Now let's think about movement in general. So now in classical mechanics, when do we know that object is moving? How do we define that? Right, change of some variables, kinetic, non-zero kinetic energy, change of the position, change of the velocity. What else? How else can we know that? How do we know that the position is changing? Right, so we monitor the object. At the 0 time it's here. At later time, even if we ignore where it is at later time, we can just look at the same spot. If it's not there anymore, that means it moved, right? Or someone moved the object, right? So probabilistically, you may think, okay, so if the probability of finding object at a certain spot at 0 time is 1, then if you turn to the same spot later and the probability of finding it there 0, that means our object moved, right? So the same fundamental idea of the movement as probability changing in time, or probability density in this case, can be extended to quantum mechanics, right? So in quantum mechanics, we can say that something is moving if probability density is a function of time. And now for these two cases, let's just check which case actually have probability density changing with time. Because in both cases, I just gave you what the wave function will look like, but I didn't tell anything about the absolute square, right? So there is an extra operation. And let's first consider stationary state, because it's easier. Stationary state. And we will understand why it is called stationary. Of course, well, you can guess that probability density will not depend on time. Okay? So how does this happen? We take this product, phi n of x, multiply by the exponent, and that's our wave function for the stationary case, and we take absolute square. So what will be the result? This is just exercises in complex numbers. Yeah. It will be a spatial part squared, right? There will be no time. Where did the time go? How did it cancel out?
It goes to 0, e to the 0 is 1.
So what's the, how do we understand this magic? So what is this absolute square, like in terms of more elementary math? If we say take the IT squared, right? So this is pretty much like if we remove other exponents or like constants, that's not essential here. What does this mean? It means we take I over t and we multiply by I over t star. That's what absolute square is. Okay? And so what happens to this when you star it? You get negative I, right? So because you just, whenever you need a star, you find I and change the sign in front of it. And, well, then you get 1, right? Because this is IT minus IT, which is 0. An exponent of 0 is 1, right? So that's the origin of that magic. That tells us that if you have a single product and you take the absolute square to get the probability density, you will get something that is time independent. And this is truly remarkable because, as you will, or maybe we'll start it today, as you will learn in quantum mechanics, there are situations where stationary state can have non-zero kinetic energy, okay? But based on the criteria of probability of finding an object, the probability is not changing with time. So based on this criterion, then you look at the object, you take your gaze away and then look again, and the object will be staying at the same time, in the same space, right? In the same region of space. But interestingly, it will have kinetic energy. So what does that mean? In classical language, if something has non-zero kinetic energy, that means velocity is non-zero, and that means the object is moving, right? So that means if you look later at the same spot, it won't be there, right? Or if it's periodic motion, well, it will just depend on how, like you may be lucky that you look exactly at the period, but if you look at a different time, it won't be there. But here in quantum mechanics, the remarkable part is that there are stationary states with non-zero kinetic energy or with non-zero angular momentum or non-zero momentum, and yet they are stationary. So there is this weirdness where two classical criteria of the motion, meaning that we say that object is moving if we cannot find it in the same place later in time, or we say it's also, we can characterize the motion by, say, non-zero kinetic energy or non-zero velocity. Those criteria are different in quantum mechanics. In quantum mechanics, something may stay at the same kind of area of space and yet have kinetic energy. Yeah?
Is that because of superposition?
No, we're considering right now here stationary state. It's not because of superposition. It's
Because if there's like two outcomes, then there's also the possibility of the combined outcome.
actually when we consider the superposition state, you see that in the superposition state, the probability density changes in time. So with the superposition state, you can say it's more classical in the sense that the superposition is how in quantum mechanics we can make things move. Stationary states do not move, all right, and there's nothing we can do about that because it's just probability density is exactly the same in time. Now, to add to this weirdness, if we start measuring what's the position of the object, right? So imagine you have probability density distributed in space, and you start measuring, okay, where is our electron or where is our particle? And this wave function will be collapsing in a certain values of the x, and we will get some random distribution of positions. So if you take the million systems and all in stationary states like 1s hydrogen atoms, million systems, and then at the same time you will measure where is our electron. So then you will find completely different random positions, and it seems like electron is moving, but in reality probability density is the same, and that randomness just comes from the fact that the position operator for that operator, the function we are investigating is not an eigenfunction. So naturally, when you want to predict the result of the measurement, there will be many eigenvalues, and the coefficients of the expansion of this function with respect to eigenfunctions, those coefficients will define the probabilities, so it will be undetermined. So, but also you can make the experiment where you have millions of the hydrogen atoms all in stationary states, probability densities are fixed in time, and then one you measure at 0 time, another you measure at later time, another you measure at even later time, right? 1 second, 2 seconds. So, of course, because of the randomness, you will be getting the results that electron behaves like as if it's moving, right? Because you will be finding it at later time in the different positions. But that is not the result of the dynamics of the probability density. It's just the result of the randomness of the measurement, of the uncertainty of the measurement, because the operator or property you're measuring is not an eigenoperator for the function you're measuring. So I hope you will understand that one day. Okay, so I'm not expecting you to understand everything I say right now, but just thinking about that sort of experiments hopefully will prompt you to ask more questions. Okay, so now more interesting situation, non-stationary. Why do we call it? Oh, here you understand. These states where you have only a single product, they're called stationary because when you consider probability density, there's no time dependence. Okay? So make no mistake, the function itself has time dependence. But the physically observable probability density does not have time dependence, okay, because of this conjugation, okay, this absolute square. Now, let's consider a more interesting case, the case where we have, say, two terms, superposition. So let's say our psi of xt is coefficient 1 will be 1 square root of 2. Instead of writing it all the time, let me just put C1 and then phi 1 minus E1t h bar plus C2 phi 2 Alright, so this is my function, and now instead of one product I have two, and C1 equal to C2 equal to 1 square root of 2. So you can do it at home if you'd like, just using these numbers. And then if we do absolute square, how many terms will we get? No, we have 2 terms in the function with square function. How many terms do we get? 4, that's right. So first bracket will be the function itself, right, plus C2. And the second bracket will be conjugated function, right? So is everyone following what I'm doing here? Right, so it's this guy is just psi, and this guy is psi star, right? So psi times psi star, that's what this symbol means, psi absolute square, right? And so now here are the 4 terms, this with this, this with this, this with this, and this with this, right? So it's 1, 2, 3, 4, right? So let's make all these products, and okay, so the first product will be timeless because the exponent here there will be positive E1, I E1, here's negative E, I E1, and so they will cancel out, and so this will have C1 square, phi 1 square. Right, so no time dependence. It's as if there are no these terms, right? So naturally we would get timeless terms. Now the 4th term is also very simple because we are multiplying again the same pair, the same functions, right? Just with conjugation. So let's say this is the term number 1, and the 4th term will be C2 square. This is 4th term. Now the interesting terms are 2 and 3 cross terms because we are multiplying the second with the conjugated first and first with conjugated second. So what we get is C1 star C2, phi 1 star phi 2, and the most important part is the exponent. Right, so we have time dependence because the energies are different for 2 different functions, unless there is such situation as degeneracy, where the function 1 and function 2, when the Hamiltonian acts on them, they give the same E. There are such situations, but they are somewhat rare. Right? So right now we don't consider it, or if there is such situation, we could just pick the different superposition, not between 1 and 2, but between 1 and 10, so that energies are indeed different. So that's why this thing we assume to be non-zero, right? And then there is a time dependence, that goes to the probability density. And the third term is conjugated second term. So it's C1, C2 star, phi1, phi2 star. And here we have this, right? So naturally, what we got is psi square is a function of time, has a like time dependence, right? And so that means probability density changes with time. On some simple examples, I will illustrate this when we look at the particular problem. We'll start with particle in a box, where I will solve time-independent Schrödinger equation. And once we have these functions, then we can play with this, construct different solutions for time-dependent Schrödinger equation and see how do they behave in time. If it's stationary, the probability density will not depend on time. Non-stationary probability density will depend on time. So we have kind of about a half an hour. I can take questions about this not very simple material, or I can, I presume you may have one or two, and then I will start, the particle in the box problem. A specific case for the time-independent Schrödinger equation solution, right? So, do you have any questions on what I just did, talked about? Yeah. Okay, so you need to understand that kinetic energy, as any other quantity in quantum mechanics, has an operator, right? And that operator is spatially, it depends on space variables. Okay, so that's, I guess, the origin of weirdness in quantum mechanics in a sense. But on the other hand, it's kind of, after some time it starts making sense, because so the kinetic energy is an operator. It is proportional to the second derivative of with respect to space variable, right? And so then if you are interested in average kinetic energy, you don't want to go to like all the decisions about whether your function is an eigenstate of the kinetic energy or not eigenstate. If you just want to understand, okay, so in average, how much of the kinetic energy do I have? So then we talked about this. You can do psi, t, psi. Presumably the psi is normalized already, so you don't need to divide it by the product of psi's in the denominator, right? So then what will this be for the stationary state? You can easily see actually that because this inner product is about the space integration, the time and the kinetic energy is the derivative with respect to space. Again, the phase factor, this part, the exponent, the time exponent of the bra and the ket, they will cancel each other and they will not contribute to kinetic energy at all. Okay, they actually won't contribute to kinetic energy per se in the non-stationary case as well, although they will create some modulations of the kinetic energy in time. So, but that's what. Let's just focus on this for now. This is a stationary case, stationary state. Okay, so then the answer will be psi n star x, right? With minus h bar squared 2m derivative acting on psi x, right? So this is your kinetic energy, and it's purely depend on what is the overlap of two functions, the original function and second derivative of the function, right? So it turns out if the function is really localized, then the second derivative is high. If it's kind of closer to the line, like the curvature is small, then you get the smaller kinetic energy. But the time, like the time exponent here, doesn't really contribute anything to the average kinetic energy, simply because kinetic energy operator is the derivative operator with respect to space, has nothing to do with time. Okay, so that's the math. Now maybe there is more physical insight you were expecting when you were asking this question. So far, that's my answer. Okay, anything else? Because they are different solutions of time-independent Schrödinger equation. Okay, so if the solutions are different, it's kind of more nature, like I would say generally the situation is that if you have different functions, then you have different eigenvalues. But there are situations, it's not we cannot exclude the case where two functions can have the same eigenvalue, right? But for the example that I'm considering here, I want the En and E2 be different, for the reason that if I end up with a special case when they are the same, then it's not very kind of interesting case for me, because I will lose the time dependence. Okay, and so I would kind of end up with a stationary case which originates from two wave functions which are degenerate in energy, right? So there are such situations, but they are very rare in reality, because this degeneracy of eigenvalues, it's really easy to break them by any small physical interaction that you bring to the system, because they usually originate, this degeneracy originates from the symmetry of the problem. And one interesting example would be if we consider double well problem. Say you have a molecule where there is a possible tunneling between the two configurations, and if it's a left-right enantiomer in some chiral molecule, this barrier is really actually high, but potentially enantiomers, if you think about them as just a certain configuration of atoms, you can always put enough energy and rearrange atoms from the one enantiomer, left one, say, to the right one. So it's just the barrier is high, and naturally that doesn't happen. But barrier is finite, so if you put enough energy, then you can pool the atoms and then recombine them in a different order. So the large barrier actually makes the situation where this phi 1 and phi 2, they correspond to kind of delocalized eigenstates of this problem, and the energy gap delta that is E1 minus E2 is actually very small, because the higher the barrier, it turns out, if you pull the barrier to infinity, pretty much you will have two independent kind of parabolas that they will have, one will have E1, another will have E2, they will be the same energy, and the gap will be exactly zero. But if the barrier is finite, that gap is slightly above the zero. What this means is that there is a process. If you start in a system in one well, say if you start with left isomer, with the time scale of the energy difference, the system will go to the different enantiomeric configuration. It's just when this barrier is high, the energy difference is small, the time scale, this oscillating exponents, they are very slowly oscillating. So it takes the time of creation of Earth or something, millions of years, in order to go from L to R, because the barrier is too high. Okay, so on the quantum level, it all comes down to the probability density, because you make the system to be in one well, and you want the system to, or ask a question whether the system will evolve in the different minimum through the tunneling, right? And that time scale of that process is dependent on the energy difference between the two eigenstates. And those eigenstates could, in these situations are very close to each other. We can illustrate this more once we will start solving the time-independent Schrödinger equation for simple systems. Then we'll have the phi functions, and I'll show you some computer simulations for the probability densities. Any more questions? Okay, if no questions, then I will just start the setup for a very important problem. Model problem, which is called particle in the box. And of course, this is a lot of material. You go home, read about it again, like review lecture, and if you have questions, let me know. But yeah, the main point was that now, for the situations where the potential doesn't depend on time, we know how to break down the time-dependent Schrödinger equation into or easily solvable time-dependent part and time-independent Schrödinger equation. And then we know how to combine the solutions of time-independent Schrödinger equation to solve the time-dependent Schrödinger equation. So the initial conditions there is a key to the right combination, and we will focus now mainly on time-independent Schrödinger equation for different systems. Now, of course, as chemists, we would like to think about molecules, but molecules are difficult in mathematical sense because there are many particles. We just discussed every particle adds 3 dimensions, right? It turns out that there is kind of easier approximate consideration for molecules, and say if we consider something like this unsaturated polyenes, right? Then a simple yet kind of insightful model one can make for this type of compounds is that to consider only p electrons, right? Consider them independently, right? And they all can kind of move within this molecule, because we know, since it's a kind of conjugated chain of the carbon atoms, then there is this easily movable electron subsystem. And so they are all we will ignore the electron-electron interaction. So then every electron can be considered independently, and every electron can be considered like being in the box of the size of the molecule. Okay, so very, very straightforward setup, right? We consider a single electron or single particle, and it's a one-dimensional or quasi-one-dimensional system. We do not account for this zigzag kind of structure, right? We are thinking about one particle on the line, essentially, between 0 and L, and outside of that range, 0 and L, the potential goes to infinity, so the electron cannot escape that prison of the molecule, right? So, and to make it mathematically simple, we will make potential go to infinity once, let me just write down this carefully. The potential term in the Hamiltonian that we will consider is a kinetic part, potential part, and the potential part is 0 when x within the range from 0 to L, and infinity otherwise, right? So once the electron, say, tries to escape from this range, then there is a penalty right away. Potential goes to infinity, so that way we kind of keep the electron within that range naturally. Okay, and then the kinetic energy term, as before, was h bar squared divided by 2 masses of the particle, second derivative with respect to x, right? And this is simply momentum operator squared divided by 2m. Right? One way or another, that's just equivalent representations. Okay? Now what we will be doing is we're going to be solving time-independent Schrödinger equation for this Hamiltonian. And this is one of the simplest problems in quantum mechanics, yet it is relevant to some of the conjugated compounds. So what it will give us is eigenspectrum, so these energies and the functions. And so from these energies, one nice quantity that we can obtain is, say, excitations. So the excitations meaning that if you have one electron sitting and having energy E1, say, then imagine light comes in and excites the electron to level E2. Both levels will be solutions of the eigenvalue problem that we'll solve, right? And so that energy difference between E2 minus E1 will correspond to the energy of light that will be absorbed. And that way you can actually figure out what will be the color of the compound, right? Because the light that we have from sun is a white light. It has many components. The components that energy of which, h mu, corresponds to energy difference. And that energy difference naturally will depend on the size of the chain, right? And the number of electrons. So then eventually you can say which out of many components of white light will be absorbed by a compound and which ones will not be absorbed but rather reflected. And so the ones that are reflected, they define the color of the compound, right? So through this you can, through this consideration, you can roughly estimate what would be the color of the compound, whether it will absorb visible light or say will absorb more in ultraviolet. That sort of questions you can address with this simple problem. Of course, it's all approximate, and so we'll see how accurate those approximations are, because for the compounds we'll consider, we also will know the exact result. But now let's consider the differential equations. One differential equation that we will be looking at is this one, right? And so the way we solve this differential equation is going to be kind of piece by piece. We have 3 regions in x coordinates. Region 1 is from minus infinity to 0, and we can also say, region 2 say in the between 0 and L, region 3 between L and plus infinity. Okay. Now, the probability density of finding particle outside of the box is 0. That's kind of is 0 when, say, x is in the region 1 or 3. And probability density is non-zero when x is within the range of within the region 2. Now, why would I say that? It's very simple. So the energy of any particle in the box, average energy, should be less than infinity, right? So it should be finite. It's like any physical particle should have finite energy. You shouldn't have infinite energy. Now, if you have a function, say, let's just estimate what's the average energy. Average energy will be function, Hamiltonian function, right? Imagine it's normalized. Then this is integral from minus infinity to plus infinity, phi star x h phi of x. Right? And so this integral you can split integral over the first region plus integral over the second region plus integral over the third region, right? Because simply these regions are from minus infinity to plus infinity, and integral is additive. All right. Now, if you have something like, if we consider first region, right, and you have function that is non-zero, so probability density is non-zero in that region, so then there will be potential in that region that is going to infinity, right? So naturally the integral cannot be kept finite, because if you have a finite probability and infinite potential, the integral will naturally goes to infinity, right? Either it's a first or third region. So the only way to keep energy finite, so the average energy be smaller than infinity, is to have everything in the second region and the probability density of the function in the first and third region to be 0. Okay, so that 0 compensates the infinite potential that we have there. So then we have average energy coming only from the second region. Okay. So once we establish this, then we can proceed to the solution in the second region. And our function will be zero if x within the first region, something x in the second region, and 0 when x in third region, right? That's what we established. Now let's write down the differential equation for the second region. So differential equation will be on the second order. So this is the kinetic energy acting on the wave function plus potential energy. But if we look at the potential energy in the second region, that's the second region, right? So potential is 0. So we have 0 multiplied by the wave function, which essentially means that we don't need to account for this term. And we have energy, some constant, multiplied by a function. Okay? So if we now rearrange some terms and I use this notation that you probably use in math classes, calculus classes, so differential equation classes, then the constants you need to consider is here. Right, so we can actually make a plus here. And that's the differential equation we need to consider, right? So second derivative of the function plus constant multiplied by a function equals to 0. And we have also some boundary conditions, meaning that the function must be 0 once it reaches the third region, and it must be 0 when it reaches the first region. Okay? Did you study how to solve the second order differential equations? Right, who knows how to solve the second order differential equations? Please, hands. Okay, one person, huh? Okay, first order differential equations? Okay, so no one really but one person studied the differential equations here? Okay, so then the Schrödinger equation will be your first one. Okay. All right, so, but you understand what the problem is, right? So the differential equations are relations between the function and its derivatives, right? Given like in the form of equation, and the question here is what this function is, right? Okay, so the typical way of solving this second order differential equation is writing a wave function as a linear combination of cosine and sine function. Why is that? Because simply when you take a second derivative of the function, you can kind of see that if your function is linear combination of sine and cosine, you will, well, cosine after differentiating twice will turn back to the cosine, and sine after differentiating twice will turn into the sine. And then you will get some constants, and here there will be also sine and cosine, and what this equation will give will produce if you substitute the function by a linear combination of sine and cosine is equation on essentially the coefficients. Okay. So that's very kind of a natural way of well, solving the second order differential equation of this type, where you have function differentiated and constant plus constant times function non-differentiated. Okay. And so it also helps to, let's say, take this k equal to the constant in front. So it's k squared. That means we have square root and since we're running out of time, let me stop here, and I will post these notes, the notes on a particle in the box online, so that you can look them up before our next meeting. And also I'll put some materials on differential equations, try to look through them, just to get the sense of what are the typical ways of solving differential equations are. And we'll resume with the particle in the box next lecture. Okay? You seem confused.